let's get back to the lectures. We found in the previous lecture that all of the three vectors k, h, and e, that is the magnetic, the electric field, and the wave vector pointing in the direction of propagation of the wave, they're all orthogonal to each other, meaning that electromagnetic waves in vacuum are transverse. And we defined what transverse polarization meant in the previous lecture. Now I want to see how much energy does a plane wave transport. And to find out that, I look at the Poynting's vector. And this is defined simply as E cross H. And since we know what E is and what H is, well then I can, first I can simplify this by inserting K cross E for H. And there's the vacuum impedance to convert from the magnetic to the electric. And I can rewrite this. Of course, I use the Levi-Civita tensor. I'm not going to go through the math, but it turns out that it's k hat over z naught E dot E. That is E square, which looks remarkably similar to the energy density in vacuum. And no, of the electric field, sorry, and minus a term that's proportional to k hat dot E. Fortunately, we know that k is orthogonal to E, meaning that this whole thing is equal to 0, meaning we're left with this term for the Poynting's vector. So now we show that not only does the wave propagate in some sense along k vector, but also that the energy that the wave is transmitting is also traveling in the k direction. And I can write it like this. There you go. And we all know the terminology quite well now. And let's see. Yeah, the impedance of free space, this set 0, what's that? Well, it's simply mu naught over epsilon naught. So it's a numerical constant, and the value is 376.8 blah 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 ohms. As you can see, it's an impedance in the same sense that a resistance is an impedance. In terms of the units, I mean. And now you also see that the numerical magnitude of H is much less than the numerical magnitude of E because Z is such a large number. Okay, and now we've seen that we have energy transport in plane waves, but there's also the case of energy density and momentum, which we discussed in detail in the previous chapter. So that's the next topic. Okay, so energy and momentum in plane waves. Okay, and we showed in chapter 8 that the energy density in the electromagnetic field is equal to the following. First, there's a term that's essentially the square of the E field. And then there's a term which is essentially the square of the magnetic field. And also we show that S is equal to the Poynting's vector, which is the energy transport through a unit area during a unit time, is equal to E cross H. And note down that these were defined assuming that the fields are real. But now we were working with the complex fields, which behave somewhat differently. And for waves, that is, if we have a dependency that looks like E2 IK minus I omega t, we take the time average of the fields when we work with the complex fields. And this is to, well, when you have a wave, of course, the energy transport varies as time goes along, because sometimes the E field is small, well, or the real part of this is small and sometimes it's large, meaning that the energy transport varies in time. But for example, when we're working with light, the phase varies very quickly. The frequency is 10 to, I don't even remember, 12, 15 hertz. It's huge, meaning that often we only work with time average, because that's the only thing we can actually measure anyway. And to take the time average, we're going to show that you can do this instead by just adding complex conjugates on the fields, meaning for example, well, to elaborate a bit, since we have quadratic terms here essentially, we can't just take the real parts after doing the square. We have to do the real part before. And then, but you can actually show that this is the time average of the Poynting's vector is equal to the following. Where the star denotes complex conjugation. So E cross H complex conjugate, that will give us the Poynting's vector. And there you see, when you do the complex conjugate, you change the sign up here. The phases of this and that cancels, and we're left with a real answer. And similarly, we can, for the electromagnetic energy density, we can add complex conjugates on each term, and we get, let's see, we just put a complex conjugate on each of on one factor in each term, and then we get the time average right out. And I'm going to show why this is the case. And first of all, we know that the energy in a real field, which is just a cosine of kr minus omega t, looks like the following: that u equals to half and this is the amplitude. There's an epsilon 0, and then there's the time variation term. Or simply the real part of the phase factor here. Then we have a similar term for the magnetic field. And a cosine of the same factors. But we know now that H0 is proportional to E0 because of the Maxwell equation coupling the electric and the magnetic field. And this will give us that, well, I use that H is equal to K cross E over the vacuum impedance. And then if I insert this, I get that U is equal to epsilon naught E naught square without the half. and the cosine square of the kr minus omega t. Okay? And the time average of this is just stuck in this cosine because epsilon 0 and E0 are constants, meaning that the time average is just going to get a factor, a numerical factor out of this guy here. So I stand still at one point in space and I take the average over one period of the cosine square. And that looks like the following. The time average over cosine square is equal to 1 over the period. Integrate from 0 to t, the period, and then cosine square all the stuff that's inside there, which you know very well. And this is just a half. And a simple mental rule to remember this is to just recall that sine square plus cosine square is equal to 1. So the time average of sine plus the time average of cosine square is also equal to 1. And because they have the same shape except a small phase difference, then they must be half each. So that's a way to quickly remember that. And now we see that u is equal to half epsilon 0 E0, where E0 is the maximum amplitude, but well, it's not the maximum amplitude that goes into the energy density, it's half the maximum amplitude square. Okay, and now for the complex fields, we can, if we try this expression here, and I try to insert the complex expressions for E, D, H, and B, I will get that the time average of the energy density in a plane wave is a quarter E dot D. That's a quarter H B. Now I insert that D is equal to epsilon 0 E and B is mu 0 B, and we get just quarter E dot epsilon 0 E. Let's see. And this is the amplitudes now, right? Because the phase factors cancel out here. And the final answer is that we just get out half epsilon naught E absolute value square. And this is exactly the same as we found for the real field case using time averaging, meaning that this is a more quick and elegant way of performing the same calculation, just exploiting that the phase factors cancels. Yes?
In the top equation for u, should cosines be squared over?
Yeah. Everything should be squared, of course, in a highly democratic fashion. Okay, any other questions? Okay, and well, you see now that this works, and the reason why it works is just that we have e to I kr minus omega t times e to minus I kr minus omega t, but because of the star you get the opposite sign and the phase factors just cancel out. And so this is a quick way of calculating those. And now we can also notice the following, that time average of S, the Poynting's vector, which we're of course interested in, it's the energy flow, is half E cross H complex conjugate. And if I now insert for H is equal to K cross E, as I did before, then I will get that we have half, one more set notes, Let's see if I get this right. Okay, so there's the vector is pointing along k hat, as it should. There's a factor z0, and it's e0 absolute value square. But this is incidentally the same as, well, it's proportional to the energy density in the plane wave, time averaged, times the velocity of the plane wave, times k hat. Meaning that it's simply the energy density in the plane wave times the velocity of the plane wave going in the direction of the plane wave. It all makes sense. Okay. Yeah, as I said, this is just the energy density times the velocity of the wave. So it's just what you expect. You can just compare this, in fact, to the current density is equal to the charge density times the velocity. Exactly the same thing. So plane waves behave very much the way you would expect them to. And in terms of units, the Poynting's vector is, of course, energy per unit volume times the velocity, meaning that we get, if I gather this into watts, we get watts per square meter. And there's also a unit which is, or a quantity which is often used called the intensity of a wave, called I. And we define that simply as the length of the Poynting's vector. The length of the time average of the Poynting's vector. And this is then just, of course, I skip the unit vector, so we get U times C. Or power per unit area. And an example of an intensity which is often quoted these days is the solar constant. And this is simply 1370 watts per square meter. And this is the energy transport through a square meter on the surface of the Earth from the sun. Meaning this is how much you would, in theory, get out if you have a 100% efficient solar panel. So it's, I think it's a fairly simple concept, but if anyone has a question on this, you should ask them now before I wipe them all out. Nothing? Okay. Okay. Now, we know that there's also momentum in the electromagnetic field, and we would expect that since there's a transport of energy in the plane waves, we would also expect transport of momentum. So what's the momentum density again? The momentum density we just defined as the following. Again, this is assuming linear media, of course, and it's S over c square. So it's a vector pointing in the same direction as the Poynting's vector, but this is not the transport, it's the density. And again, we're interested in the time average. So I insert a time average here and a complex conjugate here, and then there must be a time average there. And the magnitude of this, let's see. No, let's see. Anyway, I can write it like this. Energy density in the plane wave divided by the speed of light to power 1, since the u was s times c. And then there's k hat, the direction of the momentum density. Okay, so when light falls onto an absorbing material, the material actually feels a momentum from that light. And as an example, I found out recently by accident, more or less, that the MESSENGER probe, I'm not sure if you heard about it, it's a NASA probe to explore the planet of Mercury, which is really close to the sun. They're actually going to use gravitational assistance to slow down the probe. So if you have the sun, the planet Mercury in this orbit, and the Earth here, they're launching the probe to like this, and it's supposed to catch up with Mercury, and then gravity is going to slow it down as it passes. So you don't use fuel to slow it down when you reach the inner orbit, you use the planet's gravitational pull. And you need to get the altitude pretty accurate here, because you want to get really close to get the maximum slowdown, but you don't want to get too close, because then you slam into a mountain or something, right? Obviously. This is easier in Mercury because there's no atmosphere. The funny thing is that when they did the final orbit correction, they were quite close to the target altitude. The target altitude was about 200 kilometers, but they figured out they were about 9 kilometers off, which was sort of quite good, but it wasn't perfect. They would overshoot a bit, and you wouldn't get quite as much slowdown as you wanted. Then someone sat down and calculated, hey, how much is the radiation pressure on the solar panels this close to the sun? And they found that if they just tilted them by, I think it was about 20 degrees, then it would actually get just the orbit correction they needed to hit right on target. And then they managed to reduce the altitude by 8 kilometers to just get right on the target altitude, more or less. So you can actually use the radiation pressure or the radiation momentum. It can actually be quite important in, well, for example, in space where you don't have all these other forces that are overwhelming. Another example is something that happened to a so-called 3-axis stabilized satellite. It's just a satellite that has a stabilized position in terms of rotation. It's just a box, essentially, and you have solar wings pointing out. And I didn't manage to find out the details of this because I forgot the name of the satellite from when I heard the story. But the point was, anyway, that the solar panels were going to fold out when they got into space because it's too large to transport like this into a rocket. So these things are supposed to fold out. And on the one side, the third segment didn't fold out, meaning it had a larger area for the radiation pressure on the one side, and of course the outermost wing, meaning it got there was a torque around the center of gravity on that probe. So this in fact shortened the lifetime of the satellite by several months, because now they had to use rockets to compensate for the radiation pressure to keep it aligned in the right direction. So radiation pressure might seem really insignificant if you put in the numbers, but if you're in the right environment, it can actually be very important. Okay. Until now, we've been discussing electromagnetic waves in a pure vacuum. But to also, well, a vacuum is a very boring place, of course. But if you go to the simplest case material, then you have that if the material is linear and isotropic, then epsilon 0 goes to epsilon. Let's see. title is Electromagnetic Waves in Matter. Just the simplest case of matter, so to speak. If we let epsilon 0 go to epsilon, or epsilon r epsilon 0, and similarly for the magnetic permeability, mu 0 goes to mu, then the wave velocity becomes the following. C, let's see. Well, in vacuum you have c, the speed of light in vacuum, is equal to epsilon 0 mu 0 under the square root and in the denominator. While in matter you would have that v is equal to 1 over epsilon mu under the square root. And now if I rewrite this in terms of epsilon r and mu r, I can write that v is equal to c over epsilon r mu r under the square root. And now this is, if you remember from wave physics, this is just the index of refraction. Meaning that the index of refraction is in fact equal to the epsilon r mu r. And very often in a material that's not opaque, mu r is equal to 1, to a very good approximation. And we get that the index of refraction is essentially the square root of epsilon r. And well, if you're wondering how good an approximation this is, then you can consider, have you ever held a magnet up to a material that's been transparent, which was not then ferromagnetic? I mean, if the glass here was ferromagnetic, I could just take a magnet and put it on the glass, right? But of course it's only diamagnetic or paramagnetic, and those effects are very weak, meaning mu r is 1.000, maybe something then. While for the dielectric constant, this is frequently from, let's say, 1 to 10. Or, well, I have never seen a material with 10, but okay. Well, diamond maybe. So this depends, of course, on the frequency. So I might write that n depends on omega like this. So because there's so few transparent ferromagnets, this is often a perfect approximation when you're working in optics. And all the vacuum formulas that we've seen can be translated just like this when we have a linear isotropic material. And this means that we have the following formulas, that U time average is like this, epsilon r, just insert that. We recall that S is equal to E cross H, but that was equal to U, so now it's times the velocity. So now it's U times V, where V is just C over N. So, and yeah, V is C over N. The momentum density is now just U over V times K hat. Okay, and the intensity, that's just the absolute value of S, is in fact reduced a bit. Because the velocity of the wave is also reduced. Now, of course, this is all nice and dandy if you're inside one material, but as soon as you get to a different material, let's say if you have K vector like this, and then there's some interface over here, then at the interface I have a jump in the epsilon. There's epsilon 1 here and epsilon 2 over there. So at the interface this is not true anymore, so we need to investigate what happens then. And this is in fact something that's going to be our next topic, okay? So while it's It's perfectly fine to use this as long as we have a linear isotropic material inside one material, but when you get to an interface, well, then you have to be careful because the epsilons change very abruptly at the interface. Okay, so I think we will only have time to introduce some of the vocabulary, but we'll start now on reflection and transmission at a flat interface, which is typically a glass window, or if the curvature is very small compared to the wavelength, it could be also, let's say, a lens in, let's say, your glasses or the camera, for example. And first, to get some terminology straight, I'm going to draw a figure. This is a flat interface, even though it might not appear so. And n hat is the unit vector pointing upwards. And in the material above, I'm going to have epsilon 1, mu 1, the material constants. And in region 2, I'm going to have epsilon 2, my 2, mu 2. Let's see. So 1, 2, like this. This is called what's that called? Okay, skip that. We have light coming in here at an angle theta 0, and there's also light going out, and you all know from before, of course, that the angle is the same, but I'm going to call it the theta r, the reflection angle, and the wave vector going out I'm going to call q, because it might conceivably, before we investigate, it could be something else than k. And into the material we have a different angle, theta t, t for transmission, and a wave vector called p, like this. Now, if we have a linearly polarized source, which you might just, we can in fact just assume that, because if I looked at, we have two linear polarizations, right? If you have a wave vector traveling like this, the wave vector is pointing out like that, I could have two linear polarizations, and I can choose my coordinate system freely, of course, but let's say I choose one axis in the blackboard, then this is one of the polarizations, and then the other polarization would have to be orthogonal to this one. Let's see, I just call them E1 and E2 for now. So those are the two linear polarizations, that the field is just oscillating in one plane, or let's say two different planes, depending on which polarization I'm looking at. And this is hopefully something you've seen before. Is there something unclear about the polarization?
Yeah, I've seen this before.
Yeah, okay, great. And then if I will now investigate two different polarization cases here. And these are called the P polarization. And the P means parallel. And when I say the parallel, I mean that the E field is in the plane of incidence. So the incoming field here is in the plane of incidence, meaning that E is like this. If the plane wave is linearly polarized as shown on the figure, we say that it's P polarized. Okay. And I also have something called the S polarized. And this is when the electric field is orthogonal to the plane of incidence. Okay, and this is of course, let's see, if I just draw them on the same figure, it would just point into or out of the board, depending on the phase, of course. Okay, and the S here comes from the German word senkrecht. Which means perpendicular, meaning that the electric field is perpendicular to the plane of incidence. And to be sure to avoid any form of confusion here, the plane of incidence is defined as the plane containing the two vectors n and k. Okay, so the two vectors form a plane. So I can form a normal vector, of course, by crossing these two vectors, but that's not very often needed, perhaps. You'll notice that if I have normal incidence, meaning that k is parallel to n, like this, then the plane of incidence is not defined. So I cannot no longer define the P and the S polarization. And this is natural, of course, because then we'll have rotational symmetry, assuming that the material is rotationally symmetric or isotropic. And for now, we're going to assume that. Let's see. And the magnetic field, of course, when the electric field is S polarized, the magnetic field is parallel, and vice versa here. But we always refer to the electric field when we discuss the polarization. Okay? So when someone says that the light is polarized in this direction, then they're thinking about the E field, or the alternative is that they're just confused. Yeah. Okay, and I think that we stop now, because otherwise we'll just get started on something and then have to give up. So are there any questions on the terminology or the figures before we leave? Is this clear? Okay, see you on Wednesday.